All right. I'll get started. I will begin. I'll begin with a word of prayer. So. Dear Heavenly Father, we thank you for this day, and I thank you for this class and this time we have to meet and study your creation. Just pray that you just guide our steps today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. One of you had a question right before class about I said the book was crazy, it was impossible, but I'm wrong, because the book had an angle alpha. What problem were we talking about? Which problem was that? The exploding projectile problem, 8.96 maybe? So I said at the top it can't just drop, remember? But they had an angle variable, like a variable angle in their problem. So if you think about it, if alpha was equal to 0, then there's no vertical component. So that's their way out. Like the angle has to be 0. If it drops is all. So the book's homework problem is like stupid. Like most of the sophistication of the example I did in class, which I did make a mistake in the quadratic equation for time at the end of that example, by the way. I juxtaposed a sine for a cosine somewhere. But anyway, in short, the problem that I said in the book maybe didn't make sense. I was wrong, because the book has an angle alpha. If you put that angle alpha to be 0, then there's no vertical component to the exploding fragment. And so all of the vertical, just all the momentum is horizontal for the half the fragment afterwards, basically. The other one falls. So that is the reason the book is not wrong. So, and when I say book, I just mean the Mastering Physics homework, right? So, other questions? Comments? Nobody? All right, well, so we're talking about rotations now. And rotational motion and again, please watch the video that I sent you guys a link to, no Rickroll. And essentially there we talked about like the arc length is equal to the radius times theta. And then, I talked about the tangential speed versus the radial speed. And we looked at the tangential acceleration versus the radial acceleration and understood some relations there that aren't really new. We're just recasting some things we said about centripetal and tangential acceleration in new variables. So there's that. Please do watch that and try to digest that. But one of the things that happened ultimately in that lecture is we looked at the kinetic energy for what you could call a rigid body. But the rigid body we looked at be something like this. The sum, I equals 1 to n of 1/2 m sub I v sub I squared. And here, what I envisioned was there's some sort of like rotation axis. All right, and so all of the, like m1 is distance r1 from the axis. Maybe m2 is distance r2 from the axis. All right, I don't know, m3 is over here somewhere. Its distance r3 from the axis. So, and somehow or another, all these masses are forced to rotate, right? They're forced to rotate at the same angular speed, all right? So in that sense, all of these are rotating. I can't really draw it very well. Best thing I can think of is if you could kind of imagine a Christmas tree, and just imagine a Christmas tree rotating around its axis, right? All of the ornaments on the Christmas tree, assuming that they don't move, right? Assume they just like frozen in place. That would be kind of like this. So if you rotate the Christmas tree around, its center, then the ornaments would be rotating around that center, such that the distance from the ornament to the center trunk of the tree would be held fixed. That's the idea here. That's what I'm talking about. So in this situation, the relation between the rotational rate, the radians per unit second of the mass, and the linear velocity here would just be as follows. It'd be like VI is equal to RI times omega. So the radius, how far it is from the axis of rotation times the radius, times the radians per second times the radius would give us meters per second, the tangential speed, all right? And if we're assuming that it's fixed in place, that's the totality of the speed. The speed would just be tangential. So if you put that up into here, you get the sum I equals 1 to n of 1/2 mi ri omega quantity squared. All right? But then what happens is you can rewrite this as the sum I equals 1 to n of 1/2 mi ri squared, right? And there's an omega squared on every single term. So you can factor that. Just factor it out of the sum like so. All right? This is what's done. Now that assumes that every single mass is fixed at the same rotation rate, right? This is the case. What I mean by a rigid body. It's a body which is everything's connected. It's fixed. It's glued in place. It's forced to rotate at the same rate as all the other masses. So if that's the case, then we have this formula for the kinetic energy associated with the rotational motion. And in this situation, this quantity right here is called big I. It's the moment of inertia. Moment of inertia. Now this is the moment of inertia for a bunch of point masses that are so situated. Yeah?
Did they pull the half out to the outside as well and then just...
Oh, yes. Thank you. Thank you.
All right.
Yeah, that'll hit me in about 3 minutes. Thank you for saving me the... let's see here. Yeah, the 1/2 is supposed to come out here. Thank you. Thank you. You are correct. Oh, rats. Well, I brought the juice. That's what it's for. Let me fix that. Yeah, let's not redefine the inertia. Let's not redefine the moment of inertia to not include the to include the half just for this semester for fun. No. Not my intention. So 1/2, pull the half out. I equals 1 to n of m sub I r sub I squared. That quantity, thank you, omega squared. So this right here is I. It's the sum I equals 1 to n of m sub I r sub I squared. Now, example 1, what if you've just got like a single mass out here, right? And maybe it's rotating around the z-axis, right? Suppose it's rotating around the z-axis in a circle. What's the moment of inertia for the single mass? So for just a plain old single mass distance, let's say r, I'll use a big R, the moment of inertia would just be mr squared in this situation. Now, so to talk about moment of inertia, we need to have in mind an axis of rotation, all right? And we need to know like the distance from the axis which the mass is rotating, okay? If that same mass was rotating, you know, around the y-axis instead, right? If you can imagine that. Yeah? So if it was like, you know, whee, like that, right? Then this radius might be, I don't know, a. And then the moment of inertia here would be ma squared, right? So technically speaking, this is the moment of inertia about the z-axis, whereas this is the moment of inertia about the y-axis. Yeah? And if you were to think about some other wackadoodle axis through the origin, well then it would be different. You'd have to think about the geometry, you know? But we don't tend to do that. We just focus on nice, geometrically reasonable to understand axes of rotation. All right. Okay, so obviously we don't just want to talk about point masses. It's kind of hard to imagine a bunch of point masses forming a rigid body anyway, right? Like, I don't know. If I think it's much easier to think about, like, you know, here's a whole infinity of masses, right? Yeah.
Just to clarify on the radius, that distance is always going to be perpendicular to the axis of rotation.
That's right, perpendicular to the axis of rotation. That's the r involved, yeah. So, like this here, you could think about this as a whole infinity of masses, right? One point mass after another glued together, right? Roughly speaking, it's a uniform mass. That's not quite true because, as you know, markers are lumpy. But see, this would have a different moment of inertia if I was to consider rotating it around its end, right? At the axis that's kind of pointing at you. That would be one moment of inertia for this, whoa, system of markers. And then on the other hand, if I was to rotate it around its middle, there would be a different resistance to rotational motion, right? So moment of inertia has got to explain, in some sense, the resistance of a rigid body to start rotating. It's the rotational analog of mass. Did you see that? Maybe you can see that, start to see that already. This formula is 1/2 I omega squared, right? Compare that to 1/2 mv squared, right? So the moment of inertia is kind of playing the role of mass. Whereas the angular velocity, now omega is the angular velocity, is taking the place of velocity in this story. We'll see this as we go on. So for a continuous distribution of mass, we can talk about the moment of inertia is the integral of r squared dm. All right. So this is how we calculate the moment of inertia for a continuous distribution of mass. And in this situation, the kinetic energy of such a thing will be 1/2 I omega squared, like that. Essentially, I can go through the same argument I just went through at the start of class, but instead of having a summation, I have an integration, right? I have an integration over the mass, and I can pull out the angular velocity, I can pull out the half, and I'm just left with an integral over r squared dm over the body. And, well, what kind of integral is that? Well, that depends on what kind of body we're talking about. It could be a one-dimensional integral, it could be a two-dimensional integral. It just depends on the shape. So let's start with example 1 here. Suppose we have a uniform mass m distributed over length L. All right, and we're going to imagine, to start with, rotating it around around the end. Okay, so here's the rotation axis, and we want to calculate what's the moment of inertia for this. All right. Now, once we're done with this, we can calculate how much kinetic energy is stored in, like, say, for example, a uniform baseball bat that's swung, you know, a certain angular rate. We could figure out the kinetic energy in such a thing. So let us look here at a little bit of mass dm. All right, and we'll think about that being distance x out here. All right, so what is the moment of inertia for this little piece right here? Well, di, of course, would just be x squared dm, because x is the distance from the rotational axis. Now, how do I calculate dm? So uniform mass per unit length, right? So lambda is dm dx, which here is big M over L. And so what I'm really up against here is x squared times m over L dx. So that's the little bit of inertia that I get from this little bit of mass dm, which is found from x to x plus dx. And then I integrate this to find the total inertia. So I integral from 0 to L of m over L x squared dx. Pull the m over L out, and then we have integral from 0 to L of x squared dx. Is there a question? I keep hearing talking. Please do not talk when I'm lecturing. It is distracting to me. Thank you. X cubed over 3, evaluated from 0 to L. So then we get what? We get, I think we get m over L, and I believe L cubed over 3. So the answer is 1/3 mL cubed. So there you go. That is the moment of inertia of a, what's that? Did I put a cube? Oh no, goodness gracious. You guys gotta watch me today. I'll do stuff like that. So, yeah, sorry. Sometimes a certain amount of talking in class doesn't distract me too much, but today my mind is not right, so bear with me. Anyway, so are we good? So this is the moment of inertia of a rod rotating around its end. What would the moment of inertia be if we took the same rod, but instead rotated it around its middle? So example 2. What if we took the same mass m, but in the middle, we rotate? All right? What would the moment of inertia be around the center rather than the end? Since moment of inertia is defined by an integral, and integrals are additive, we can break it into the moment of inertia for the left half and the moment of inertia for the right half, and we can add them. Okay, so like if I have mass m, that means I've got what? I've got like m over 2 here, right? And this distance is what? L over 2. Whatever the moment of inertia is for that half, we should just double it, right? By symmetry here. So the moment of inertia in this situation is twice times what? 1/3. Mass is m over 2 here. And what's my L? L over 2, right? Squared. So I'm using example 1 to do example 2. Okay? And what's that work out to? I think I got a 1/12 ml squared here. Yeah? So it does make a pretty significant difference, right? So in other words, the moment of inertia of a given, like, say, ruler, like a yardstick, right? If you swing it around its end, the moment of inertia is 4 times bigger as opposed to if you just spin it around its center. Yeah. And so if we had the same rotation rate, the kinetic energy in the ruler spun around its end would be 4 times the kinetic energy if you spun it around its center, if we had the same rotation rate, right? A different question you could ask is, how should the rotation rates of these two rulers be related? If you want to have the same kinetic energy for spinning it around the end as you do spinning it around the middle, how should you relate? How should the rotation rates relate, right? So like, suppose on the one situation I've got the ruler like this with omega 1, and I've got this one, like this with omega 2, and I want them to have the same kinetic energy. How does the omegas have to be related? Well, the same mass. So we have 1/3 ml squared omega 1 squared is 1/12 ml squared omega 2 squared. That's the relation, right? So the m's and the l's, they cancel, and what you get is that omega 1 squared is 1/4 omega 2 squared, right? Which tells me that omega 1 can just be equal to omega 2 divided by 2. That's cool.
Where'd the 1/2 go? Like the kinetic energy.
Oh yeah, fair enough. I did mean to cancel those out. You're right. I should put the half there. That's important. That's important for when we merge the rotational kinetic energy idea with our linear kinetic energy. All right. We'll soon talk about that, but not just yet. Oops. But the halves cancel. Fair enough. So I would have to double the rotational rate to get the same kinetic energy if I'm spinning it around the middle. Okay, so there's that. So if you understand these two examples, then you can, you can do more interesting ones, right? Like, for instance, hypothetical guys, like example 3. I'm not going to work it out, but let's just talk about it. What if you had a wagon wheel, right? And you had 1, 2, 3, 4, 5, 6, 7, 8, spokes, each with radius r, right? And then you've got this outer band out here, which is relatively thin. It's usually metal or something, right? And so that's also essentially at r. Basically, we got like big mass at r equals to r from the, and of course you know where the rotation of axis is going to be for the wagon wheel. Let's say the center. Let's not be weird. Let's put the axis through the middle of the wheel. Then you can ask the question like, what's the moment of inertia for this wheel? How would you do it? So you need to know like the mass of each spoke. Let's suppose that the mass of the spoke is m. So the way you do it is you'd calculate the moment of inertia for each spoke, multiply that by 8, and then add it to the moment of inertia for the rim. What's the moment of inertia for the rim? We don't need integration for this, right? If you think about every single possible little bit of mass that comprises the rim, it's all the same distance from the rotation axis, right? So the moment of inertia, you think about any little bit of mass out here, dm, it's all the same distance. It's all distance r, right? So when you do that integral of r squared, dm over the rim, you just get big M r squared. It's the same formula as for a point mass because the totality of that mass distribution is all distance r from the rotation. So the moment of inertia for the wagon wheel would be the moment of inertia for the rim plus 8 times basically the moment of inertia for like example 1, right? Because every one of the spokes is rotating around its end. Yeah? So I think example 1 and example 2 are kind of boring on their lonesome, but you can put these examples together to do much more interesting problems. And see, now that we know the moment of inertia for a wagon wheel, you can figure out what's the kinetic energy bound up in rotating a wagon wheel. Yeah? And then you could do other fun stuff, like think about a wagon wheel rolling down a hill. If it rolls without slipping, then the energy of the wheel has 2 parts. It's got the rotational part, and it's got the translational part. So you'd have like 1/2 mv squared plus 1/2 I omega squared for such a rolling wagon wheel down a hill. So we'll do problems like that. But at the moment, I'm focused on deriving some formulas for moments of inertia. So let us move on. So next up here, this one's really kind of stupid. Example 4. And we are, I think, in lecture 26 now-ish. I do have more notes for you guys, which I will publish soon. I'm sorry it's slow coming, but... So this one's very silly. So suppose you have like a cylindrical shell. So a cylindrical shell means that, you know, we're not so much interested in the thickness of the shell, let's say. Is it like a kind of a thin shell? Thin cylindrical shell, all right. And we're going to talk about the radial axis through the center, right? Talking about the moment of inertia relative to that axis, and so this distance is r, all right. So in that situation, what's the moment of inertia? If it's, you know, total mass m. I would just be what? It's all distance r from the rotation axis, so the answer is just mr squared in this situation. What if instead of this just being a shell, though, what if we had a solid cylinder, right? What if you had a cylinder, let me make it a little bit bigger, like this, right? So now the thickness is r, but this is a solid cylinder of radius r. And again, we want to find the moment of inertia about the axis through the center of the cylinder. What should we do now to figure out the moment of inertia of such a thing? I can't just say mr squared anymore, right? Because some of the mass is further from the rotation axis than others, right? So the way we figure this out is we chop it up into a bunch of simple cylinders. See, because basically you want to use the method of cylinders and think about like a cylindrical shell, radius r, let's say little r, right? And we know the moment of inertia for such a little shell inside. So this shell, a little shell, what should the thickness of the shell be then? So the thickness of the shell would be dr, all right? So what is the volume of such a cylindrical shell? So like dV would be something like, you know, 2 pi r dr times L. That would be the volume of such a cylindrical shell. I take the circumference times the thickness. That gives me basically the area of that little circular ribbon. And then I multiply by the length to get the volume. So I'm supposing that the length of the cylinder we're talking about is L. All right. We're also going to assume that the total mass is m again. And furthermore, we're going to assume that the mass is uniform in its density. Okay. So if we have m uniformly distributed, what does that mean? That means that the density, right, which is dm dv, the mass per unit volume, is also equal to m over the total volume. What's the total volume of the cylinder? I have a cylinder, length L, radius R. What's the volume? Yeah?
To clarify, is dV for volume or what?
Volume, yeah.
Why is it dV?
Because it's an infinitesimal volume. We're talking about generically speaking, density is defined to be mass per unit volume, so it's dm dv, which in principle can be a function of the position. Here we're assuming a uniform mass density, so I can relate the infinitesimal mass per unit volume to be equal to the total mass per unit for total volume. That's the uniform assumption. So like m total mass divided by the total volume here is what? It's pi r squared, that's the area, right, times the length. So pi r squared times L, that's the volume here. total mass over total volume. So what that tells me is that the little bit of mass, excuse me, dm, we actually get formula for it. You solve for dm here, basically. I've got m over pi r squared L times dv, but my dv is 2 pi rl dr. So that is the amount of mass that is in a cylindrical shell of thickness dr at distance r from the rotation axis. Now the reason I'm cutting, why am I cutting this shape up into cylindrical shells? Why? Why would I do that? To what?
Integration.
To do integration. What's my goal here? My goal here is to calculate the moment of inertia for the solid cylinder. All right, this is like a continuation of example 4 in some sense. So we already know that the moment of inertia for like the red cylinder is nothing more than what? It's nothing more than di is, it's nothing more than, you know, r squared dm. I mean, that's what it is, because the totality of the red cylindrical slice is at radius r from the center. So to calculate the moment of inertia, I just have to add up I have to add these up. So I integrate r squared dm. But you see, r squared is r squared dm we have over here. Can we simplify that? Ooh, I think the L's, they be canceling. What else we got here? Pi's cancel. Help me out here. So we got what? M little r. M little r. I think I got a 2. 2 survives, right? dr. And the pi's, they be canceling. I think we got an r squared, right? Do the units on that make sense? Quick check. Is this dimensionally consistent as a formula? Behold, we have got a mass over here. Over here, I've got a mass times a length divided by a length squared. That's net units of kilograms, so yay. Mass is mass. That's good. If that wasn't the case, I know I would have made a mistake somewhere. So, okay, so here we go. We go, excuse me, 2m, big M, RDR, RDR, divided by big R squared. And what are we doing? We're adding up the inertia. What? The sum is over what? It's the sum over the shells, ranging from little r equals to 0 all the way out to little r equal to big R. So this integration must be taken from 0 to r. And then big R. And then you integrate. What do you get? Well, let me pull the constants out. So we've got a 2, a big M. We got a big R squared down there. And it looks like I've got a R cubed, right? See, R squared times R cubed. R cubed integrates to R to the 4th divided by 4. Evaluated from 0. Now that's not too bad an integral, is it? Let's see here. Surely you've done worse things in Calculus 2 this semester. We're like,
With respect to f?
no, I mean, no, I'm not differentiating. So this is the infinitesimal method. This is just a template for how to set up the integral over dm. So anyway, this is the same technique we use to calculate volumes in Calculus 1. So anyway, what do we got? 2 over 4 is a half. Whoa, after all this is the formula. 1/2 mr squared. That's not too bad. So for a solid cylinder, right? For a solid cylinder, the moment of inertia is 1/2 mr squared, assuming uniform density. The difference between example 4 and example 5, example 4, we're talking about the mass distributed from the axis all the way out uniformly, whereas in example 4, the mass is all at radius r. So radius 5, example 5, a smooth distribution of mass from the axis out, you know, like it's a big tube of cheese or something, or it's a hot dog. I don't know. What do you want? What do you want from me? Cheese. Cheese. Is it a Costco hot dog?
I can get behind the Costco hot dog, right?
Yeah.
I only know one Costco hot dog. Unfortunately, they're family, but it's because they choked on them as a child. So
I see.
strong.
All right, so one more of these to derive, and then I'll stop calculusing you. Let's see here. So the other example that we're often fond of using is sphere. We like to talk about spheres rolling, things like that. So it's helpful to have the formula for the moment of inertia of a sphere rotating around its axis. Now this one takes us a little bit more work. Example 6, I suppose. Let's talk about a sphere rotating about a diameter. What's a diameter? So it's what? Two radiuses? Yeah. So the diameter is going to be, go straight through the North Pole to the South Pole, something like that, right? So here's my axis. We're rotating around a diameter. So a diameter is a line which goes through the center of the sphere. I feel like it's a line segment, I suppose. But I want to think about the axis being straight through the center of the sphere. Let's calculate the moment of inertia of a sphere, assuming, again, a uniform mass density. Now, if it's a spherical shell, what's the moment of inertia? Wouldn't it just be mr squared? It's a lie. There's a big difference between a sphere and a cylinder. Cylinder rotated around the axis, right? If it's a cylindrical shell, it's all a distance r from the rotation, right? If you were to rotate, if this was actually a spherical shell, and you were to rotate it around the axis, we'd have to think harder about what that means, because not all of the mass is the equatorial distance of r away from the rotation, right? The equator's distance r from the rotational axis, but not the poles. So the poles gives you less inertia than the equator, if we were just to think about a spherical shell, right? We'll talk about spherical shell some other day, like not today. I'm going to talk about the solid sphere, to be clear, solid sphere.
Do we have to compare with respect to some sort of y rate?
Respect to some sort of y.
X equals some sort of function.
Well, I think what we want to do is we want to think about something like this, maybe. So what I'm trying to say here is, well, let me leave this kind of two-dimensional. Let me attempt to draw perspective over here. So I'm talking about like taking a cylindrical shell inside the sphere, because the reason I want to do that is that all has distance r from the axis. So then I can calculate the moment of inertia for the shell pretty simply, right? The question, though, is how is that related? Let's see, I'm trying to use the same coordinates I used in my notes. I guess I used h, whatever. Okay, so here's the deal. If we pick the center of the sphere, so I like to just look at the plane where the cylinder intersects the sphere, just to have a nice concrete two-dimensional picture to sort of hang my hat on the formulas for. So this distance here is r. That's the radius of the sphere, all right? We're thinking in particular about the shell radius r from the axis of rotation, right? And then I've called this h in the notes. What would you guys like to call this distance here? We could go with h, we could go with y, go with z, whatever. What's that? H is fine? Okay. So h is a variable, little r is a variable, right? But what we always know is that little r squared plus h squared equals to big R squared, right? And we could derive various other relations. I'm just throwing that out there. We know that, okay? That's the relation between the distance of the shell from the rotation axis and the height of the shell in that sense. All right. So then the question is, what's the volume? What's the volume of this cylindrical shell? What's a dV? So you could think about taking it and just laying it out flat. You'd have like a slab, right? The thickness of the slab, if you think about laying it out flat, the thickness of the slab would be dr, right? Then what would the, my picture's not quite to scale. I'm trying to, imagine that this distance is 2h, right? How long would, if this is the 2h side, right? Because you go h up and h down, yeah? What would the other side be? 2r? Nope. It's a circle of radius little r, right? So 2 pi r is what we're looking for. The circumference, 2 pi r. So the area of the slab would be 2h times 2 pi r. That's the area of the slab. The thickness of the slab is dr, so dr. That gives me the volume. That's the little bit of volume that's subtended by this infinitesimal shell. And so that is 4 pi rh dr. Great. Now, rho, the volume density, dm dv, is equal to, well, we're assuming uniform, right? So this is also equal to the mass divided by the total volume of the sphere. What's the total volume of a sphere? You guys have worked this out somewhere. 3/4 pi r cubed is almost right. I'll take your 3/4 and trade you a 4/3. So 4/3 pi r cubed would be correct, though. Yeah. Which can be derived by a very similar integral, by the way. So there we go. Apparently dm is, what is it? M over 4/3 pi r cubed times dv. But my dv is 4 pi rh dr. Some things cancel, right? Like the 4's cancel. Anything else? Oh, pi cancels. The 3 comes upstairs, right? So I got 3 big M. 3 big M what? 3 big M RH dr. RH dr divided by what? R cubed. Okay, great. Now that's just the infinitesimal mass that's subtended by this slice, right? What's the moment of inertia for the slice? The whole reason we took a cylindrical slice is so that we can write down the moment of inertia for the slice. Di is simply r squared dm, which apparently is 3m over big R cubed h. Now at this point we should put in what h is. What is h equal to?
The square root of capital R squared minus the r squared.
Very good. So the square root of capital R squared minus little r squared, and that's my h, and then we got dr. All right. So all that's left now to do is to add it up, right? So I, for a sphere, solid sphere, about a diameter, is the integral. And what should I integrate from? What does r range from?
0 to some.
0 to little, no, 0 to big R.
0 to big R. What do you guys think? Is that right? Or should we go minus r to, or should we go minus r to r? What do you guys think?
0 to r.
0 to r, right? Because it can't be minus r to r, because we're already taking into account the lower half, right? Because we wrote this 2h over here, right? So I'm indexing the shell by r. But you can imagine taking such a shell from r equal to 0 all the way on down to the equatorial shell, which is really, really fat, but really, really short in height, you know. It's practically a band. What do we going to call that thing? So yeah, 0 to big R. So 0 to big R of 3m over big R cubed, little r cubed, square root of r squared minus little r squared dr. If I haven't made a silly mistake somewhere. No, that's what I got before. And so a way to do this integral is a u substitution. You can make this right here your u equal to big R squared minus little r squared. All right? And what's that make my du? This marker's dead. Too much. Thank you. Thank you for the assist in the back. What's that? So du is minus 2r dr. And when u is equal to 0, when r is equal to 0, u is equal to r squared. When little r is equal to big R, u is equal to 0. So it flips the bounds and it changes them a bit. And I've got my 3m over r cubed. R squared is what? R squared is big R squared minus u. So I have big R squared minus u times the square root of u. What's that? So what I'm doing here is I'm putting r dr is minus du over 2. So what I'm doing is I'm taking one of the r, I got an r cubed, right? So I take an r squared and I put it into the r squared minus u. The other r I'm putting into the r dr, which I switch to a minus du over 2. All right? And so minus du over 2. And then what happens? I mean, I got to work it out, right? I calculate very badly at the bottom of the board. Let me move. Let me switch over here to the top. Get out of your way. Oh, yowzers. All right, so we have the inertia is, let's flip the bounds. We've got 0 to r squared. And we've got that 3m over, I'm going to put the 2 out front, 2r cubed. And then I've got big R squared, square root of u, minus u to the 3/2 du. So I integrate, and I've got a 3m over 2, r.
How do we go from flipping 0, like to 0 r squared to the bottom of that one to flipping it back up and now?
I had a minus in the du I've absorbed into flipping the bounds. So I've got r squared, u to the 3/2 divided by 2/3 minus u to the 5/2 divided by 2/5. All evaluated from 0 to r squared. So if you look at that, what you got is a 3/2 m over r. And this gives me a 3/2 r. Let's see, what happens when we put like an r squared into that? What is r squared to the 3/2? It's r cubed, right? Huh. So I get r squared times, is that r to the 5th?
Yes.
Oh, wait a minute. Hold on a second. Hold on.
What have you done?
Flag on the play. I gotta keep this r cubed out here. That's still r cubed, because I kept the r squared here, my bad. So we've got r to the power 5 minus 5 halves. Again, r to the power 5. All right, so we've got r to the power 5 divided by r to the power cubed. What's 3 halves minus 5 halves? Oh man. Where'd I do? What's that? Oh, I'm a dummy. Come on, we divide by what? 2/3? No, idiot. 3 halves. 5 halves. Duh. So this is a 2/3 and a 2/5. Oh, there, that's better. What's 2/3 minus 2/5? It is not negative. It's 10 fifteenths minus 6 fifteenths, also known as 4 fifteenths. If I calculated that right, 4 fifteenths times 3 halves, mr squared, which is what? 2/5 mr squared. That is the moment of inertia for a sphere. If it is a spherical shell instead, I think it works out to, it's either 4/5 or 3/5. I can't remember off the top of my head, but I'll have to look into it for you guys. Anyway, there is a table of these things in the book, of course, but I hope I've showed you how these things are derived. You can derive them too, if you know calculus, and you do. I'll see you guys Wednesday, except that I won't, because as you know, it's assessment day.